Hello everyone, today we'll talk about the solution to the problem modify graph edge weights. The code is pretty long, but we'll go through it step by step. In this problem, essentially we have a weighted, undirected graph. Some edges are already given some weights. Between other pairs of nodes maybe there are no edges possible, but the most important part is that between some edges we can create an edge with any positive weight that we want, integer positive weight. And we want to do it in such a way that the shortest distance from source to destination is equal to exactly some target that we're given. The statement is a bit different because it gives us some edges with weight of -1 and we have to convert those weights independently to some positive weights such that the shortest path is equal to target, but you can think of that operation as just adding edges between those pairs of nodes with any positive weight that we want, and of course if we get that weight to be very big, it's as if that edge didn't exist, because it will not influence the shortest path from source to destination. Of course, this problem is a variation on the shortest path problem, which is typically solved using Dijkstra's algorithm, and we'll solve it using Dijkstra's algorithm. So if you're unfamiliar with that, then of course that's a prerequisite to solve this problem, because the difficulty, of course, here is that, well, it's not clear at first what Dijkstra to run or what Dijkstra's to run to actually solve this problem. Now, the basic idea here is that if we can, for instance, find the path, we have this source, of course, some destination, so source destination, and we can, for instance, treat all the edges that we have control over as not existing. And in that case, if there is a path from source to destination which is shorter than target, there is nothing we can do to make that path longer. And in that case, it's impossible for us to change weights of those edges, to add those edges in any way to make the shortest path equal to target, right? Because the shortest path that's shorter than target will exist no matter what we add to the graph. Likewise, if we take all the edges and add them to the graph with the smallest weight possible, so with weight equal to 1, then we expect the shortest path from source to destination, of course, to exist. Now, if it exists and it's already equal to target, then we're happy. We can add all our edges with weights equal to 1. But it might also not be equal to target, and it's only good if it's smaller than target at this point. Because now maybe we can take some of those edges and make them more expensive to push the cost upwards. And in particular, of course, and here of course we see that previous special case, because if that shortest path does not use any edge that we add, and it's still smaller than target, then it's impossible for us to do anything about it. But if it has some edge that we have control over, so for instance, it has this edge here that we have control over, then we should probably make that edge more expensive. And of course, maybe if we make it more expensive, probably the amount is such that this path now has exactly cost target. Maybe we're happy and this is still the shortest path, and that's it. But it's also possible that now the shortest path is not this, but the shortest path is something like this. And maybe now we have control over this, or over this. So it might be that after changing an edge, some other path becomes the shortest path. But of course that other shortest path still has less than target, the length less than target. So we can keep doing that. And it's easy to see that if we keep doing that, then every edge that we have control over will be touched at most once. So that is one solution which probably will pass tests if you implement it correctly, to just do it, make all the edges equal to 1, and then always make sure that you increase the weight of an edge to what it would be for the whole path to be equal to target, and do it until finally the shortest path is exactly equal to target. And you have to do that for every edge that you have control over in the pessimistic case. But it's also possible to solve this problem in 2 runs of Dijkstra's algorithm, if we can make sure that after changing this edge, there is no situation where we go now through some other edges to have path shorter than the path after changing this edge that we have control over. And the central idea here is to, of course, first find those shortest paths starting from our beginning vertex, assuming that all the nodes, that all the edges that we have control over have weight 1, and that should be shorter than target. But also now we can try to make sure that when we change this edge, we change it in such a way that now that path is exactly correct. Of course, assuming that we change it to a value greater than 1. So in order to do so, we might imagine also the graph where all the edges that we have control over have weights equal to infinity, and start going backwards from the destination. Because in that case we know what is the shortest path from any node, if it's of course possible to reach destination, but we have a guarantee that it's possible. But we have for every node the shortest path from that node to destination, which is the same thing as the shortest path from destination to that node, that utilizes only the original edges, no edges that we can add. And in that case, we know what change we should make to the weight of the current edge that we're looking at to make sure that the weight of the path is correct, because that change is such that the length of this path plus the length of this path plus this is equal to target, and the length of this path will be taken as the length assuming all the edges are set to infinity. But that is still not enough to ensure that everything is going fine. What we also need to do is to find the shortest path in the graph, which assumes that all the edges that we can add have weight 1, and change them step by step, trying to change them to make the length of the path correct. Specifically, it's necessary to do it that way, because in this case, we can make sure, because of course we can make sure that there is no point to go through any edge more than once on the shortest path. That's just true. We do not want any cycles. If we have a cycle on the shortest path, then we can just not go through that cycle, make it shorter by that cycle, and the path will become shorter because weights are positive. And in that case, the only edges that will not be equal to infinity are some starting edges here with weight 1, maybe, but we know that we only visit them at this point, and we will visit them, so this is the best time to visit them. One edge that has weight greater than 1, maybe, and we'll visit it at this point, we'll not visit it again, and all the other edges have weight infinity, and in that case, indeed, the path from this vertex on the path to destination is exactly as if all the edges that we have control over are equal to infinity. Feel free to meditate on it or look at the implementation to maybe iron out some rough edges when it comes to the understanding. But yeah, this problem is pretty tough, and actually probably rigoristically proving that the solution works is difficult, and it's possible that it maybe isn't correct, in which case if you find a counterexample, then feel free to add it to the test cases, because the solution passes all the test cases. And now we have the code. Now that code has 3 parts: the Dijkstra part, which is here, the boilerplate, and finally the algorithm. Our boilerplate just defines infinity and defines our adjacency matrix in the standard way, because we'll be running Dijkstra in n squared, so on the adjacency matrix. And now our Dijkstra, we have one function to calculate both the distances and the paths. The paths are calculated in the standard way, where whenever we update the distance to a given node, we remember which previous node updated it. So that's the previous array, the parent array. And we'll be maintaining all the visited nodes, this parent previous array, and the distances. At first, all the distances are infinity, other than source, which has distance 0. And the standard n squared Dijkstra does the following n times, because every time it adds a new node to the cloud of already calculated nodes. It finds a candidate node that is not visited yet, but it has the smallest possible distance calculated from all the nodes. So at first it will be source, and then the algorithm will keep going on. We mark it as visited, and now we look at all the edges that go from it, and update the distances of all the nodes that are, of course, touched by an edge from that node. And we just do it by iterating through all the neighbors. We try to change the distance to that neighbor that we already know to the distance to that closest not processed node, plus the edge weight between closest and neighbor. And that edge weight here will be once equal to 1, once equal to infinity, depending on which direction we run our Dijkstra. So this is just controlled by change2. And of course, if we have improved, then now the distance is better. We remember that distance, and we remember that the node that realizes that distance, so the previous node on the path from source, is equal to this closest. So this is the standard n squared Dijkstra. And finally, the algorithm. So we go from source assuming that all the edges are equal to 1, and we go from the destination assuming all the edges are equal to infinity. And now those are the edge cases. So if the shortest path is too long, even if we make all the edges that we have control over as cheap as possible, or if there exists a path that does not use any edges that we have control over, and it is shorter than target, then we cannot get rid of that path. We return an empty array, because we're asked to return the empty array. Of course, that's most of the difficulty of the problem, because if the problem was just, is it possible to change them in such a way that the shortest path will have length that's equal to exactly target, then the problem would be much simpler, but we have to constructively show one such instantiation of the weights. Now we reconstruct the path. So backwards from destination, we append the previous node, and we now reverse the path. So we start from the source, and we remember what we currently went through. So every edge that we go over will increase that weight. And now for every weight that we have control over, we have to set it to the rest of the path to destination, so the distance from destination to our current node, assuming that all the other edges are infinity. Of course, minus the destination, the distance that we have already traveled, and the whole sum should be equal to target. So in essence, it's target minus from destination minus current dist. And of course, v is the next step on our path, u is the previous step, so we are traversing the edge between u and v. So if that's an edge that we have control over, we have to set it to some value, at least equal to 1. Otherwise, we just take its value. And if at that point we set it to a value greater than 1, then this is our opportunity to end running the algorithm, because now we know that this path will be equal. Now we have, because of course we have assumed that all the edges have weight equal to 1, so we have made some change. After that change, this path has now exactly the value that it should have, because this is target minus, so exactly after setting the value of that edge to this expression, the whole path will have the cost equal to target, by definition. And now we set all the other edges to be equal to infinity. So all the edges that are not yet set still have a -1, we set to infinity. And at the end, since the problem asks us to give an instantiation, give the values to all the edges, we just return our edges.